Welcome back to the Moonshot channel, where we use the engineering design process to solve cool problems using modern technology. In the last episode, we formulated our problem statement and pulled together our design requirements for the problem of predicting the track of hurricanes. In this episode, we'll get into the concept generation phase, or more specifically, brainstorming. Just like with a scientific method, we're going to have to do a lot of experimentation as we work our way towards our final design. The ideas we come up with in this phase are each akin to a different scientific hypothesis. They're unproven and will require some testing to determine their viability. But that happens later. For now, our task is to come up with as many of these possible solutions as we can and hope that if we do things right, one of these ideas will be worth pursuing. This is also where creativity has its greatest influence on the design we end up developing. Doing this right can mean the difference between coming up with a truly revolutionary invention and making something that's just a small incremental improvement on an existing idea. Now, regardless of whether you're interested in learning about artificial intelligence, or if you're just trying to learn how to solve problems more effectively, there's a lot that can be gained from studying how the human mind works. The first point I want to make on that front is that while genetics define our individual intelligence potential, study after study has shown that the environment, which includes everything from nutrition to education, is responsible for how much of that potential we realize. What's more, while our intellect generally levels out for the most part during our teenage years, recent studies have shown that it may be possible to improve certain aspects of our intelligence later in life, such as working memory, which aids our ability to solve abstract problems. And even more research shows that our creative abilities can also be enhanced in certain ways. There's a very famous neuroscientist named Dr. David Eagleman, who put out a fantastic 6-part PBS series a few years back called The Brain, detailing the inner workings of our mind. He did this in a very approachable way, much like Cosmos did for astrophysics. And just a few weeks ago, he released a new documentary on Netflix called The Creative Brain, which also it kind of expands on the theory behind the cognitive revolution that is the foundation of the book Sapiens, which is apparently required reading these days, throughout the Silicon Valley and the tech industry as a whole. Creativity, or rather our ability to come up with abstract ideas and imagine things that don't yet exist, plays a core role, along with our working memory and our ability to formulate multi-step solutions to problems. After all, brainstorming is a key step to problem solving, and creativity is the main driver behind brainstorming. Now, in this documentary, Dr. Eagleman follows some of the most creative minds in the English-speaking world and uses them to illustrate how our brains come up with creative ideas. I highly recommend watching this for yourself. But there were a few key takeaways that Dr. Eagleman lays out for inspiring creativity that I think are going to be very relevant to our brainstorming. The first is to try something new. Get off the path of least resistance, as he calls it. One of his subjects changed careers to gain inspiration. Another, a famous inventor named Nathan Marvold, who Bill Gates once described as the smartest person you'd ever met, routinely jumps between very different sorts of activities, like nuclear physics and cooking. Second, push boundaries. Creative ideas exist in a balance between the familiar and the new. Figure out where the line between what works and what doesn't is. Think of ideas that you know will work. Then think of some completely ludicrous ones and try to figure out where the line between them is. This can help you break the mold of convention. One of Dr. Eagleman's subjects uses an interesting technique involving flip books of random images that he jumps through so he can break free of a train of thought. Others try things that push societal norms by making music intentionally off-tempo or out of tune, or make things that are provocative in some way. This can lead to thinking of ideas that may not have come to you like in any other way. In fact, David Eagleman goes on to showcase how this approach was used by a school that was on the brink of being shut down They introduced art into every class from math to science and found that by having students do art and then go and do whatever the core subject was or incorporate art in some way, they were able to do better at those core tests within each of those subjects. And finally, accept failure. Almost nobody succeeds the first time they try to do something. And experimentation is not only required in both science and engineering, but failure is one of the places where we get our inspiration for new ideas. We try something and then it doesn't work, but perhaps it gives us a clue that leads us to a new idea or new concept, which we try and possibly fail again with, but get closer than we did last time. Or perhaps we didn't learn anything from that round, other than what clearly doesn't work. A good engineer needs to accept failure and be willing to just let it roll off their shoulders so they can move on to the next thing. Once you try enough things, you may start to see patterns, or may start to see something like on the fringe of each of these failures that leads you to that one successful solution. Anyway, this documentary was quite well timed for this episode, as all three of the above concepts are incorporated in nearly every one of the leading brainstorming techniques out there. Brainstorming is all about creativity. Now, there are a lot of different approaches that engineers have come up with over the years to brainstorm, and a lot more that were borrowed from other professions as well. But the technique I learned in college has worked fairly well for me over the years, so I'm going to go with that here. It's a traditional form of brainstorming resembling Osborne's method, which dates all the way back to the 30s. With this method, there are a few ground rules. First, go for quantity. Spit out anything and everything that comes to mind, no matter how nonsensical it may sound. Next, withhold criticism. Remember Dr. Eagleman's advice on pushing through your fear of failure. Well, it's a lot easier to do that if nobody thinks their ideas will be shot down out of hand. Brainstorming needs to be done in a safe space where people feel comfortable saying anything that comes to mind. To that end is rule number 3, welcome wild ideas. This is just like Dr. Eagleman's note on pushing our boundaries. The wilder the ideas on our list, the more creative our solutions may get. In fact, if an idea makes you do a double take, maybe linger on it for a few minutes and mull it over. Ride that train of thought as far as it'll take you. Next, combine and improve ideas. The goal with all the previous rules is to spark inspiration in ourselves and others. Nonsensical ideas may be hard-pressed to even loosely relate to the problem at hand, but they may spark a more relevant idea either in yourself or your teammate, which in turn may spark yet another idea which may be more or less relevant. But the idea here is that you want to get everything you can on paper and just keep rolling. Don't start thinking of the ideas on the board as your ideas or their ideas. They're our ideas. And we're supposed to think about ways of combining them. This is a team exercise. And finally, don't fear silence. It may seem awkward, but don't call a premature end to the session. Sometimes people just need a minute or two to let the next thought come to them. Perhaps when the room goes quiet, put up that random image generator and see if you get some inspiration that way. Now, in terms of specific procedures, I actually think that looser and more casual is better for this part. But there are numerous philosophies out there, so experiment around and see what works best for you. Team dynamics and personality play a huge role. If you've got a team of close-knit people who've been working together for years, you may not need a more formal process, but if you're working with people who have never met before, a more formal brainstorming process may help make people more comfortable and get people speaking. Now, for the sake of time and because it's just me here, and I don't need to worry about teammates, I'm going to keep things very simple and use the same tool from last time, FreeMind, to basically draw my brainstorming session via mind map. But really, you can write these ideas down any way you want. Just get them on paper, a Word document, a piece of paper, whatever. Your choice, as long as everything that you write is visible to everyone in the room. Also, somebody should act as the facilitator for the session. This person is usually also the note taker, working on a big whiteboard or a smart screen. but just make sure that the person is a quick enough writer or typer to spare sufficient time and focus for the facilitation effort, as well as to contribute themselves. The facilitator needs to make sure that everyone has a chance to speak here. Introverts are very creative thinkers, or can be, but almost by definition, they like to think before they speak. Extroverts, on the other hand, have no problem, speaking their stream of consciousness out loud. But what this can mean is that introverts could still be mulling an idea over that's up on the board from a few minutes ago, while extroverts have moved on 5 ideas farther. So it's important for the facilitator to realize this and revisit old ideas on the board, ask the more quiet people in the group if they have any ideas, be a little more proactive, and just keep everyone comfortable. You don't want to put anyone on the spot, but if there's a lull in the conversation and we're just all looking at the board, no one's speaking, maybe go around the room and just ask, hey, John, do you have any ideas, or whatever. Just go around and just try to prompt people to speak up. Also revisit some of the older ideas and say, okay, we haven't talked about this in a while. Anybody got any ideas? Does this spark any thoughts? So that can help really get the introverts a little bit more involved. Also, be aware I did the brainstorming session in 2 parts. The first part I did before researching any of the existing ideas that I discussed in the last episode. But I did that after I created the preliminary problem statement. I knew I wanted to use machine learning to some degree to increase the accuracy of predicting hurricanes, but I didn't know what others were doing yet. So my hope was that doing this brainstorming would let me kind of think a little out of the box and not be so grounded to the existing solutions. Then I did a second round of brainstorming that built on my first after learning what others had tried. But before I jump into that session here, I'm going to spend a couple minutes covering the research that I did on some of the more unconventional ideas from my first round of brainstorming. I didn't really touch on that in the last episode. I wanted to have a little bit of a surprise for you guys. So we'll have a brief intermission in the brainstorming to discuss some of that and like the research that I dug up. And with that, let's begin. So I gotta think of some ways we can do this. Now, I know, I haven't done any of the research yet, which was intentional because I don't want to bias my thinking here. But I do know just from my own experience that there are a few different standard weather models out there that work in with basically physics-based engines. So meteorologists have gone and coded up the entire atmosphere. They have sensor readings and whatnot that feed into these models that measure different pressure systems moving around the world. So I'm going to put that type of system, call it physics-based systems, physics-based models, I'll call it, up here. That's one type. Now, obviously, we could probably also do this with machine learning. If we have data, we can train a neural network or a support vector machine or a myriad of other types of algorithms to do the same basic thing. What else could we do? I mean, there could be a statistical model. What else? Maybe a hybrid model that takes a combination of one or more of these and sticks them together, or different types of each and does that. That's all I can think of offhand as like high-level categories. I'm going to try to just drag these around so I can keep this somewhat symmetric. All right, so physics-based models, just while I'm thinking of it, these are based on massive data sets feeding into supercomputers and whatever that churn away. I mean, it's probably similar to what do you call them? Computational fluid dynamics. I remember I took a class on that back in grad school, or undergrad actually. It was very difficult. Machine learning, we could have a few different approaches here. We could use support vector machines, we can use neural networks. And within neural networks, there's convolutional neural networks, there's recurrent neural networks, there's just, you know, standard, like dense layers with different activation functions that use numerical data. I mean, there are all kinds of different structures that don't fit into these easy categories. There's also reinforcement learning. The latest thing are these generative adversarial networks. But a hybrid model, you know, could be a combination of any of these. A machine learning model actually could have a physics-based model and a statistical model feeding into it, and then it could output, you know, whatever. It like looks and sees, all right, well, in this situation, the stats model is more accurate. In this situation, the physics model is more accurate, whatever. So it could be used to enhance it. I do like the idea of that. But regardless of any of this, I need to start thinking about data sources. So I'm just going to put an extra branch. I mean, this isn't really a different thing. This relates to any of these, really. So data sources. And I'm just going to start putting them down. Okay, so we have land-based weather stations. We have weather balloons. We have buoys. Aircraft, I think they provide, I mean, they must have. I know that there are pressure sensors and whatnot. I mean, all these aircraft must have that. Whether or not that data is readily available is another question. But we can put that up. Ships, same thing. Out in the middle of the ocean. These might be the only way that we can get data. I can't imagine we have an anchored buoy out in the middle of the ocean, although I could be wrong. What else? Oh, satellites. Now, this makes me think about imagery. I mean, we get different types of data from satellites, but we can get image data. I mean, they could have, you know, sensors like lasers that could take readings at different points and figure out what temperatures are on the ocean surface or the tops of clouds, or maybe they can have some sort of different frequency laser that can actually go through a cloud and see the sea surface, or I don't know what, but maybe there's like temperature data from some sort of sensor. What else could there be? Well, I'm going to say infrared. This is a type of image, so I'm going to throw that within here. Now, are there any alternative sources? I mean, is that all the standard? I got to think. It's all I can think of offhand. But maybe maybe there's some alternative data sources that we could use. Such as, all right, well, they say that animals can feel storms coming. Now, whether or not that's just a pressure, you know, the inner ear feeling a pressure drop, or, you know, their skin feeling extra moisture, or maybe their eyes seeing that the sky is darkening. I don't know. But animal behavior, perhaps. Now, I'm thinking of like dogs and horses, but I don't know. I don't have a clue how we would get any data from them. Are there any other animals that we could potentially use here that might have some behavior changes that could be observed somehow if a storm were coming? I am going to say maybe. I know that we have GPS tag certain animals. Let me see, like wolves. I know there are GPS tags on wolves in national parks, but they're not really near the ocean. So I want to think of something maybe closer to where hurricanes may be. Well, what about something in the water, like fish or dolphins, turtles? I don't know. Okay, in the sky, birds. Now, also just kind of thinking about, what is it that drives animals to be able to see a storm or feel a storm coming? Is there any way that we could just get that straight sensor data? Now, these land-based weather stations and all these other sensors are getting us a lot of interesting information. But, what if it's cloud cover, like the color that we're seeing, not just clouds, but the type of clouds? So that has me thinking, I'm gonna actually put another one here. Radar can see clouds. I don't know if it can tell the type of cloud, but a camera could. So let's say webcams. I know that, from my own experience, I like to kite surf, and whenever I'm out near the water, you can look up usually these beach cams and see what the current surf conditions are, various locations around the world. So I wonder if there's a way to feed into those and see what the color of the sky is. Yeah, I mean, that's an interesting idea. So I'll put that there. I mean, these could be webcams at land-based weather stations or on their own. I don't know. I'm just gonna leave it there. What else do we have? I don't know. But this does have me thinking. I really like the idea of machine learning. I've been fascinated by it for a really long time. So my inclination, I'm certainly going to be exploring the machine learning route here. Data sources, the data sources that go with it. I mean, I almost feel like physics-based model. That's cool. This can feed into any of these. I'm not gonna limit myself here. This is almost like a separate tree, though. But anyway, this is a good start, I think. I need to do some research, because some of these ideas are pretty out of the box. But maybe they can lead me somewhere. I just need to go do some research, figure out what people have tried. If anything, if there's been any similar research along the lines of using any of these alternative data sources, especially animal behaviors, or any other sort of alternative data source that I could potentially use. I wonder if, do people, human behavior, I mean, we're animals, and maybe our subconscious is able to detect in some way if a storm is coming, and maybe that changes human behavior in some way. I don't know if it'd be enough to detect, to use, but just think about it. Like traffic patterns, shopping patterns, Not shopping, shipping. Shopping. Shopping? Yeah, shopping patterns. Oh, you know what? I just thought of one other thing that I want to look into before we move on here. One other possible alternative data source. I'm going to say seismic sensors. Can we hear storms through them? This would be absolutely fascinating. I don't know if it's possible, but it's strange enough that it might just work. So I'm going to put that up there. I'm trying to think of anything else, but I mean, I think this is weird enough to roll with here. So now we got some stuff that we can go and research. I'm going to go get to it, and we'll be back in a bit to finish this brainstorming session. So I'm just going to quickly go over some of the more interesting stuff that I found related to my the ideas I came up with during the first brainstorming session here. I'm not going to cover anything from the last episode that had to do with basically the machine learning and statistical and physics-based models that I'd already kind of discussed. This is more just what I had found that was a little bit more obscure related to some of those other trains of thoughts. So the first thing I want to cover real quick here is this interesting seismic system that was built. I mean, as well, code that was written, I should say, that was able to essentially, forecast or estimate the intensity of hurricanes. So it comes with this cool animation. You hit play, and there's a lot of movement here you can see associated with weather and whatnot. You might think at first glance here that this is something having to do with ocean currents that are able to be sort of visualized from seismic data, but that's actually not what's happening. This is really just satellite image data and some sort of weather model data from NOAA that's being visualized. And the seismic data is actually the sound in the background. So it's a little misleading, I think, showing this as the graph to go along, or the visual aid, I should say, to go along with this headline here. But it's still interesting, reading about this. The fact that you can really hear a hurricane. I want to kind of fast forward to Sandy. I don't know if you can, I think the sound may be coming through. Here we go. So yeah, I don't know if you're able to hear that increase in the sound, but clearly there was some sort of anomaly in the sound waves here associated with Hurricane Sandy. And there are other hurricanes that are coming and going throughout the season. Sandy it caused a lot of damage, but it wasn't even that big a storm at the time when it hit. So really the intensity of other storms, especially those way out in the ocean, may be louder. So anyway, this is, I thought, pretty cool, but it's not necessarily something that I think I can use just yet. I'd have to dig in more to the data and see if I can find the seismograph data that was used originally to construct this, at least the sound from this, and see if I can get it for multiple stations around the world. And then I'd need to figure out if there's a way, to sort of feed that in to some sort of, I don't know, algorithm that can construct hurricanes from it. I doubt it. Maybe that's all unnecessary. If I have the track data and I have the raw data feeds, the neural network can kind of connect the dots. But anyway, it's interesting. It's definitely food for thought. The next thing I found was Birdcast. And I'm visiting this site, today on May 1st, 2019. But originally, I found this, a few months ago when I did this brainstorming. And this does look like it's updated a bit since then. But the main takeaway here that I wanted to show was this. So apparently radar is able to see birds. And you can view the migratory paths of birds throughout the day. I mean, here, this is 10-minute snapshots, and you can see, there's a lot of movement by birds throughout the course of a day. And, they've superimposed on here, I'm guessing, some sort of wind speed indicator. But it's still, really, really interesting. If we can get this data and somehow use it along with our hurricane track data, this may be very usable. The only problem that I'm seeing with it, though, is that it's not going over the ocean. I mean, I know radar should, in theory, at least get a little ways off the coast, but these radar systems aren't able to see all the way out into the middle of the ocean, or at least they can't see birds that far away. So when I go and look at where this data came from, I'm not entirely convinced that this is going to be as useful as some of the satellite data at this point, or certainly the weather station data, but it is something to look at a little bit more. So after I get through my brainstorming, I may return to this and try to dig in a bit more if this makes it to my sort of final 3 ideas that I start doing some feasibility analysis on. But for now, I'm going to kind of put this aside and, just kind of keep it on the back burner. What I also wanted to point out that this led me, first to this list of publications from the same site. And you can see there are a lot of really interesting papers that have been written where the effects of climate and wind are being used to show bird behavior. I'm wondering if the inverse there could be true, using bird behavior to teach us something about wind. And when you dig into some of the data sources that they use, a lot of them point to this NextRad data, and NextRad data is pretty cool. Let me see, where can I? Here we are. So it's easily accessible. I can go and just visualize it here. I can go to the new version of their interactive tool, and you can see the current radar coverage. Now, one thing I want to point out is if I put this max radar ranges layer on the map, hopefully this doesn't take too long. Now you can see that, yeah, indeed, these radar stations don't see that far out into the ocean. And there's also a huge gap. So this is obviously only American, like United States weather stations. We don't have anything from Cuba, Mexico, Dominican Republic, Haiti. I'm sure, down here, South America. So even if we could use this data, it is limited in terms of its coverage. So I don't know. This is definitely food for thought, but it's not necessarily something that I am putting at the top of my priority list at this time. I am going to go back to brainstorm a little bit more, and think this over, mull it over, along with some of the other more conventional data sources, and we'll see where we go. Okay, so I've looked into a lot of this, and it is interesting. People actually have been able to use seismic sensors to forecast storms, not forecast, but to observe the intensity of storms. So I'm gonna go and pop this in here. Now, again, we're focused on the track, and then everything I've found here had to do with the intensity, but it's still really interesting. So research shows can be used to measure intensity. So that is really cool. And I'm wondering if maybe I can even go back to my problem statement and add intensity as well. Since in my research I also found that the current systems can do both. They both measure track and intensity. Not all the models. Some models measure just track, some just intensity. But it's interesting. And I want to go and add in the existing research that I found. So there are these physics-based models that work in numerous different ways. So I'm going to go and just first insert in the baseline. This is the baseline, and it's the Clipper model. That's what it was, Clipper 5. So that's the one that we need to kind of look at and sort of measure at our performance against. But it's not state of the art. I'm going to put that, not state of the art. The state of the art is something else. We'll have to do a little bit more research into that, but I know that the National Hurricane Center provides data on all the models, at least the ones that they track, so we can measure our system against that. So I'm actually gonna go and add in a parent to this verification data. So we'll use this as our baseline to compare against. And on here, I saw there was the Clipper 5, and there were several others. So we'll be checking those out. Now, there were also statistical models, as well as hybrid models of physics and stats models that were all within the National Hurricane Center sort of library. So I'm just going to go and kind of clean this up. Currently used. Just to kind of make this a little bit easier to read. And within machine learning, there were a couple interesting approaches that I covered, I think in the last time. So we'll have all that data or that information somewhere so you can see it. But we found there were these interesting models that used it's sort of like a hybrid approach of using satellite image data along with track data. And there were other ones that did a hybrid approach of using, what was it called? Reanalysis data. Reanalysis data along with track data. So those were both interesting. They both were built with neural networks. So, perhaps I should just put these up here. Well, actually, you know what? I'm going to go and do a hybrid branch. And then I'm going to move this to here. So that reanalysis data is interesting because, it essentially takes a bunch of different data sources and feeds them into this sort of aggregation model that then spits out like a grid of pressures and temperatures and all that stuff. And that gridded data then feeds into the traditional physics-based and statistical-based models so that they can come up with their forecasts. But obviously the location of weather balloons and ships and aircraft change. So, you know, we couldn't just have that feed in, and, you know, we need to put it all on a grid. And that's what some of these systems do. So I'm just gonna actually, within here, aggregated, like, gridded data. Just want to make sure I take a note of that. That's what we're gonna have to use if we go with machine learning, especially because I just don't know how I would pull in a bunch of different land-based weather stations along with all these other sources that could potentially be moving and have this thing actually learn something reasonable. So there were a couple different versions of this. I mean, it's generally reanalysis or whatever data, but I'm able to get it either through NOAA or through, I think it was like EU, but there was somewhere in Europe that provided this the data set that was used in this paper that I found that talks about using a hybrid model. However, that was pretty expensive. So, I mean, the NOAA one's free. I'm not going to get critical of any of these ideas at this point, but it's just what I found. So, anyway, I'm kind of thinking about, like, what I could do. I really like the idea of going with a convolutional neural network using, like, satellite image data as an input. You know, or maybe something else. I mean, if it's gridded data in general, this could be converted essentially into an image, and we can feed that into a convolutional neural network and have it learn that way. You know, even if it's not a JPEG, say, output, an image, if we have a grid, we can create an image. So I'm going to think about that a bit. I actually think there may be a way. You know, when you take a JPEG, it's like, you know, let me within here, just while I'm thinking. Like a JPEG is like a combination of different channels, like red, green, and blue typically. But like if I have aggregated gridded data and there's pressure, there's temperature, there's wind speed, there's whatever else, wave height, I don't know. Each of those could possibly be a channel. The output image would be gibberish to us. It's not something that would make sense. But perhaps we could make a multi-channel, you know, JPEG or whatever with, you know, pressure and temperature, wind, etc. And then that then feeds into our convolutional neural network. So I'll say, you know, the JPEG aggregated input. I don't know if there's a way to draw on here. That would be kind of, I'd really like to draw a line between here and here. But that's where I'm kind of thinking. This is an interesting idea. I'm gonna keep that in mind and maybe come up with some formalized approach. I'm gonna write that up, I should say. Also, oh, I almost forgot, with the seismic sensor data as well as the bird data. So there's actually a fair amount of research done that shows that you can see these birds with radar systems and see the migratory patterns of those. I don't know how readily available that is. My preliminary research shows it may not be readily available, or I may not be able to go back far enough to use it with alongside some of this other data, but it would be really cool if I could. So I want to look into that a little bit more. Can see with the radar. even track migratory patterns. But, you know, we have to look into so my plan is I'm going to email the researchers behind this one study I found that used radar data to track birds and see if this data is something that can be accessed or if it can be found live. If it can't be used live, then this is kind of moot. But if it can be, then awesome. Same thing with the seismic data. Well, I first have to decide, you know, so they were only able to see the intensity of the storms. If we have sensors all around the world, I do wonder, I mean, we can pinpoint earthquakes. Could we pinpoint hurricanes? I want to look into that some more. I mean, this is very promising as an alternative data input, but I need to look into it more. Also, there was, let me just, while I'm thinking about it, the track data. This is what everybody uses. In fact, there was just a regular neural network that was trained based on pure just track data that actually was able to forecast with reasonable accuracy where these storms were going based on nothing but where it had been. So that was really interesting, and that's, I think, why this hybrid model may have worked so well. So I want to definitely keep the track data explicitly listed on here and make sure that I tie that into whatever I end up going with, or at least test it out. So we have a bunch of data sources. We have a bunch of different machine learning algorithms we could use. Oh, on here, I actually forgot. There's another one that I really like, random forests. That could be very useful here. It depends on the data format, but if we can actually use, if we have numerical data, a random forest could be used to, you know, figure out like feature importance. Say we have more data than we know what to do with, random forest can help trim it down so we figure out what's important and what's not. There are other ways of doing that, statistical methods mostly, but random forests are just so easy to implement. And they do work pretty well, at least when you've got such a huge data set to work with that you don't know what to do with it, and it would take hundreds of hours to look at pairs of variables and figure out what's correlated with what or whatever. Random forests are just so easy to use. So I am going to keep that up there as an option. And they also do work fairly well for prediction too. So anyway, this is all looking pretty good. I think I have a start here. I have some alternative routes. I have different algorithms I can mix and match with different data sources. So from here, I need to basically just go and formalize what I would conceive as my top 3 or 4 options, and then look into the feasibility of using them. So that's going to be next episode. This wraps up, I think, our brainstorming. I'm trying to think. Now, I will note that if you're doing this for your own problem, you should probably give this some time. I sat around for a while after I stopped recording part 1, and after I'd done some of the research and just kind of thought. So this is me catching up with a fair amount of that thinking, you know, and getting it all written down on paper, which is why I was able to move fairly quickly here. But if you're doing a brainstorming session with teammates, just you know, make sure that you give yourself sufficient time to think, and you don't just end the session too early. So anyway, with that, I'm gonna just throw it back to me, live me, and let's wrap this up. Thank you very much, disembodied me from the past. All right, well, with that said, I think we've got some really interesting seeds to work with here. None of these are by any means a fleshed out idea or even close to a preliminary design that we can move forward with. You know, we have some ideas about different algorithms, support vector machines, or neural networks and different types of neural networks that we might be able to use. We have ideas about like what sorts of data sets are out there. But in terms of which data sets would work best with which neural network structure, or which other type of machine learning algorithm, that's something that is going to have to wait till next time. So what we're going to do in the next episode is get into feasibility analysis of our sort of top ideas. We'll take what we've done here in the brainstorming session and start mixing and matching data sets with algorithms and do a little bit more. I mean, I don't want to call it brainstorming, but more thinking about which of these might work. This is where we'll actually start getting critical of these ideas. We may also dig a little bit more into the data sets that are available to us, and possibly, I don't want to make any promises yet, but possibly get into some coding. We'll see. If it's easy enough for us to do a very quick, crude, initial, very, very loose bit of coding to test a combination of an algorithm with a data set, we'll do that. But it may have to wait till later in the process. But anyway, I'm going to see what I can do. I know that a lot of you are eager to start seeing some code get written here and get into the actual AI portion of this. After all, I think it's pretty much in the description from the first episode that's where we're going here. So spoiler alert, we're going to be using one or more neural network architectures, maybe even another type of machine learning algorithm to predict the track of hurricanes. But in terms of like the details of that, we still have a lot of work to do. So next episode, I'm going to try my best to keep it under an hour. You can see that these episodes are getting a little bit longer. I was really hoping I'd be able to keep them down under 30 minutes each, but that did not work out well. But I'll see if I can keep them down to at least under an hour from here on out. And we're getting there. That's all I can say, is we're getting there, and the problem is pretty cool. So hopefully this isn't painful to watch and you're having as good a time as me. And with that said, all right, I'll see you next time. Moonshot out.